Hello, thank you everyone for joining today. My colleague Robin and I are going to speak to you about floating offshore substations and how we've addressed some of the challenges associated with those using multi-objective design optimization. So this is a brief agenda of what we're planning to talk to you about today. We'll start with me explaining the concept of the floating offshore substation and why it's required. We'll talk a bit about the design criteria and a brief introduction to multi-objective design optimization. I'll then hand over to Robin, who's going to talk you through the parametric design and analysis model that we've generated. The effective topsides acceleration on the steel weight is the first sensitivity he'll speak on, and the second will be around optimization of a mooring system for varying water depths. I'd like to start by introducing the concept of a floating offshore substation and why it's required. Typically, floating substations are going to be required for deeper water wind farms as they get progressively larger, much like they are for fixed wind farms. The critical element to a floating wind farm, though, is that they can operate in much deeper water than their fixed counterparts, but fundamentally they're required for the same purpose, which is transmittal of the power back to shore. The concept that we focused on is the one up on screen here. It's a very simple 4-leg semi-submersible structure with 8 mooring lines or 12 mooring lines, depending on the configuration that we've looked at, and the dynamic cables coming off it. The reason we focused on this is it's quite a simple and elegant and likely solution that floating offshore substations will take, and so it was a really good subject for us to build a multi-objective optimization workflow around. It's also quite simple flat plate construction, and so from a fabrication perspective, it can be fabricated in many locations around the world, and it's suitable for a wide range of water depths. So touching a little bit now on what we've done with that substation substructure in the multi-objective design optimization process. So introducing how that comes about, we've got a fairly simple analogy on what optimization is all about. So we've got an example here. It's nothing to do with substations, which talks about how do we reduce the time it takes us to get to work whilst minimizing our pollution. There are lots of options of getting to work. Some are quicker than others. You can walk, go on a bike or a boat, a train, or maybe an aeroplane. The time gets lower as you go through that, and the pollution generally gets higher. But none of these are optimal solutions. What you really want to do is minimize your time whilst minimizing your pollution. So you want to drive yourself towards that left bottom hand corner. So instead of walking, you can run, or you can go on a bike. You can get a faster sailing boat or a power boat. You can go on the train, or you can get a fighter jet. All of these solutions are closer to optimal solutions than the first set, and as you can see, they're squeezing towards this corner. But there's only so fast a boat or a train or a plane can go, and so you find yourself limited by what's called the Pareto front, which is the line on these two axes where optimal solutions sit. So it represents your optimal solution, and that's really, from a design perspective, what you want to be driving towards. Is a design on this line. Okay, so over to Robin to talk about how we've applied that on floating offshore substations.
Thanks, Ed. So yeah, I'm going to run through a couple of examples of how we've applied that. So I'm going to present 2 studies that we've performed. The first is a global sizing study where we're optimizing the main dimensions of the platform with 2 targets. So firstly, to try and minimize the steel weight, and secondly, to minimize the topside accelerations. So these are two conflicting criteria, and the purpose of this study is to try and target the ideal level of performance of a platform balanced against the cost of the platform. So the motion performance of the platform is important for a number of reasons. It can affect the operability and the accessibility of the platform. And it's also important for setting the design criteria for sensitive topside equipment like transformers, which are often bespoke. So what we're aiming to do here is generate a Pareto front, which would allow us to find the most efficient trade-off between the platform steel weight and the allowable accelerations. So as discussed, the analysis is set up with a number of variable parameters, which the optimization tool can modify in order to converge on the optimum set of solutions. And in this example, where we're aiming to minimize both the steel weight and the topside accelerations, the parameters that we can vary are the column spacing, the column width and breadth, the pontoon length and the pontoon breadth, the pontoon depth, and the column length. So we've really got quite a number of variables that we can consider in just one study. And these parameters allow us, or the tool, to tune the hydrostatics, the hydrodynamic, and the structural performance of the platform. We also need to impose a number of constraints and criteria which the platform must meet for it to be considered a viable solution. So what does this process look like? And what analysis are we actually performing? So this is a brief overview of sort of a flow chart of how the tool implements the process. For each design iteration, the software selects values for each of our variables. The tool then loads tool sets to calculate, first of all, the platform stability, then the displacement and the through life ballast requirements for the platform. It then estimates the steel weight and calculates a mass distribution for the platform. Based on that information, it then performs a hydrodynamic analysis for each and every configuration of platform that we're looking at. And then it performs a spectral analysis to calculate the most probable maximum motions and accelerations experienced by the topsides. It then checks against the criteria that we've outlined, and it learns from the existing designs and tries to iterate towards the solution with a lower steel weight and a lower acceleration. So in our example here, we're optimizing for steel weight and specifically the heave acceleration. And this figure shows all of the designs that the software has produced, where each point represents an individual viable design. So initially, the distribution of designs will have been pretty random, and you can see all the designs off to the right-hand side. And each of these, they would work, but they're not very optimal. So as the software learns what produces the optimum design, it begins to cluster around that area and produces the Pareto front, which Ed introduced to us. So what can we learn from a study like this? Well, we can learn that we can pretty easily achieve accelerations between sort of 1.2 and 1.8 meters per second squared. But if we're looking to impose stricter criteria, we can do it, but it's going to be expensive in terms of steel weight. Or we'd need to change something about our configuration, something that is sort of beyond the variables that we have allowed the tool to modify here. We can also interestingly see that by relaxing our acceleration limit to above 1.6 meters per second squared, we'd provide only a fairly minimal benefit to the steel weight. So it's not going to be worthwhile for the transformer manufacturer, for example, to spend a lot of effort designing and producing a transformer which could withstand accelerations up to, say, 2 meters per second squared. The second study, which I'm going to introduce to you is a mooring design study that we've performed. And in this, we're looking to optimize the catenary mooring system based on the cost. So in this study, we've looked at how the cost of the mooring system varies with the water depth. And I think one of the biggest challenges for floating offshore wind is just going to be getting the first few commercial scale fields built and operate. It's inevitable that the cost of the first few developments is going to be relatively high, but it's going to come down over time, as we've seen with fixed offshore wind. But we want to try and mitigate these high costs as much as possible by choosing the best sites for the first developments. And it's not necessarily the case that the shallower sites have the lower cost, as we'll see from the study. We're also going to consider the implications of the anchor radius on the mooring system. And we've had a number of conversations with developers, and one of the largest challenges that they're facing is in consenting. There's a lot of pressure to try and reduce the mooring footprint, even if that comes at a penalty in terms of cost. So we wanted to try and work out exactly what the implications of the anchor radius are on the cost of the mooring system as a whole. So as Ed introduced, this design is for a 4-bundle catenary mooring chain system, where we have 1 bundle for each of the columns. And the variables that the toolset is able to modify for the mooring system is the anchor radius, the number of mooring lines per bundle, and the diameter of the mooring chain. The criteria that the mooring system must meet is that there must be no vertical load at the anchor. The combined mean and dynamic mooring tensions must meet code utilization requirements. And the mooring system must meet the damage requirements for single line failure. And then this study is performed for 9 different water depths, ranging from 40 meters to 200 meters. And this is to try and cover all of the expected water depths for the first commercial scale developments. So we're considering a single platform configuration for this, with a length and breadth of 55 meters and a topside capacity of 1,900 tons, which is quite representative for a 240 megawatt transformer capacity. Again, for each iteration, the software selects the mooring variables. It then calculates the mooring line tensions due to the mean forces. Then additionally, the mooring line tensions due to the wave-induced motion. The mooring line utilization check is then performed, and the software iterates towards more optimum solutions, which in this case are lower cost solutions. So the first study is considering the influence of the water depth, and I've not included the full data set for all of the mooring configurations here. Many thousands of design iterations have been produced, and this is just a processed summary plot to help us draw conclusions. The plot we have here is showing the minimum bundle cost for each of the water depths. And what we found is that we were unable to generate any viable solutions below 40 meter water depth using the simple catenary system. Would be possible, but not with the configuration we have here. We then found that the cost reduces to a minimum at 80 to 100 meters before increasing with water depth, which is a pretty useful conclusion in terms of finding the optimum site or optimum location within a site. So we know that at shallower water depth, it's difficult to design a mooring system which provides the required restoring force before the line effectively becomes taut. But it's pretty useful to be able to know when that occurs. So the other interesting conclusion is that the cheapest solution switches from a 3-line system at shallow water depths to a 2-line system at water depths over sort of 140 meters. And this again is because the extra weight of the chain is required to provide the required restoring force at shallower depths. And to achieve this, it's cheaper to use 3 smaller lines than it is to use 2 larger lines. So the second study is considering the influence of the anchor radius on the cost of a system. And this plot is showing the minimum bundle costs for each of the anchor radiuses. So in the previous slide, we were simply looking at the cheapest overall solution for each water depth. But this is allowing us to expand on that. So the different colors of the points represent the different water depths. And essentially, this is just showing us the points on the close to the Pareto front for each water depth. And you can see that we generally have a smoother set of points at the lower bundle costs. And this is because the software has identified these as more optimum solutions and generated more designs in this area. And what we see is that we can do quite a lot to reduce the anchor radius without really increasing the cost of the system too significantly. So for example, if we look at a 160-meter water depth case, and if we consider the point with the minimum bundle cost, we can reduce the radius by sort of a quarter or a third with only a very moderate increase in cost. But if we wanted to increase the radius much further, we very rapidly see an increase in the cost of a mooring system. And we'd probably have to look at a slightly different configuration, such as a semi-taut mooring system or something along those lines. So this approach, it allows us a really deep understanding of the design space, and to investigate the implications that changes in the design criteria can have. So, for example, if you have a location with varying bathymetry and you're able to move the substation from a location, say, of 60-meter water depth to a location with 80 or 100-meter water depth, you can reduce the cost of the mooring system by a third, which is a pretty interesting conclusion, and it could be slightly counterintuitive. So understanding how the cost of a system varies with water depth is very important for site selection, and as floating offshore wind develops. It's easy to make the assumption that floating wind development should sort of start in sites where the water depth is a bit too deep for fixed offshore wind and then move progressively into deeper water. But from our studies, that doesn't appear to be the best approach, and you're more likely to have sort of an easier time if you start at a more optimal water depth in the region of 100 meters. So MODOT allows us to very rapidly redesign, and in the example here, we can redesign for varying topside capacity, environmental conditions, water depths, number of array cables, air gaps, kind of the list goes on. And this gives us a really good understanding of the relative costs of components for a floating substation and wind farm. And it allows us to highlight where effort is most worthwhile to target to optimize the system as a whole.